This is section 1.4, and it has a number of objectives. A, determining if a given number is a solution to an inequality. We learned to write about interval notation for the solution set or the graph of an inequality. Then we'll be solving inequalities using the addition principle and the multiplication principle, much like we've used it for equations, and then graphing the solution set, graphing the inequality. And then we'll be applying this to some problems where we need to translate word problems into inequalities. We begin with the definition of an inequality. So an inequality is a sentence or algebraic expression that contains these inequality symbols: less than, greater than, less than or equal, greater than or equal, or not equal. And just as we learned about equations, that the solutions to equations, they're solutions of an inequality. And so here it says that any replacement or value for the variable that makes an inequality true is called the solution of the inequality. So in other words, it's very similar to what we had when we talked about equations. The set of all solutions is called the solution set. That should sound familiar. And when all of the solutions of an inequality have been found, we say we have solved the inequality. So this is important terminology, and we will apply that right away to some examples. We begin by determining whether a given number is a solution of the inequality. So number 1, it says 3 minus x less than 2. So that means when we replace x with 8, then we ask ourselves, is that still a true statement? So in other words, this then becomes 3 minus 8 less than 2. Is that a true statement? 3 minus 8 is minus 5. And of course, we know that minus 5 is less than 2. If you look at the number line, minus 5 is to the left of 2, so that means it is less than 2. So we can say this is a true, this is true, x is a solution to this equation. Similarly, if we look at the next inequality, 3x plus 2 is greater than negative 1. When we replace x with the number minus 2, we now have 3 times negative 2 plus 2. Is that greater than negative 1? Well, 3 times minus 2 is minus 6. And minus 6 plus 2, is that greater than negative 1? Well, minus 6 plus 2 is negative 4. And is minus 4 greater than negative 1? And that is a false statement because minus 4 is to the left of negative 1. So it is less than negative 1. So this is false. And then the last one, here we have 3x plus 2 is less than or equal to 4x minus 3. And we are supposed to replace x with the number 5. So that means 3 times 5 plus 2 less than or equal to 4 times 5 minus 3. Well, 3 times 5 is 15. 15 plus 2. Is that less than or equal to 4 times 5, which is 20, minus 3? Well, 15 plus 2 is 17. And 20 minus 3 is 17. And 17 is less than or equal to 17. In this case, it's the equal. I'm sorry, I'm just looking at this. This was a false, so number 2 was a false. So this is certainly a true statement. So the first one was true, the second one was false, and the third one is true also. So this is a true statement. So I would recommend, if this was not all that clear to you, then do the exercise yourself. It's also in the book, so it's easily accessible, and you can work on this on your own. Next, we're going to look at intervals and how they can be represented. And so here we're looking at interval notation, in set notation, and in terms of a graph. So a comma b with parentheses means a set of all x such that a is less than x and x is less than b. So this vertical line is where the set of all x such that x represents this. And then for the graph, we have a line here that indicates the interval. And notice that there are parentheses that limits the interval. So, similarly, when we have brackets, a comma b, that means the set of all x such that a is less than or equal to x and x is less than or equal to b. So now we are including the endpoints. And so in a similar way, we now use brackets to limit the interval in the graph. So we have a bracket here and a bracket there. Then we can have a combination. The interval including a and to b, not including b, that would be the set of all x such that a is less than or equal to x and x is less than b. So in other words, b is not included, the endpoint is not included. And so now we have a bracket here where the point A is, and a parenthesis where B is. And by the way, these things all matter. And then we can have it the other way around, the interval from A to B including B. So that's the set of all x such that A is less than x and x is less than or equal to B. So here the endpoint B is included. And in the graph then we have A with a parenthesis because that endpoint is not included, and b with a bracket where the endpoint is included. So these are all finite intervals. Next we're going to look at infinite intervals. And so here we have the interval from a to infinity. That symbol means infinity. And so that's a set of all x such that x is greater than a. So here a is not included. And so we have a parenthesis at a, and then the arrow goes all the way out, indicating it continues indefinitely. So that would be one of the infinite intervals. Similarly, when we have the endpoint a included, we have a bracket where a is, and then infinity. And by the way, infinity always has a parenthesis. It never has a bracket. And the reason why is that infinity is not a real number, so it cannot be included in the set. So the set notation would say that the set of all x such that x is greater than or equal to a. So a is included. We have a bracket for a, and again the arrow goes all the way out to infinity. That is the symbolism for that. Then when we have a negative infinity, it's like minus infinity to b, and notice that there's a parenthesis there. So in other words, the set of all x such that x is less than b. So in other words, b itself is not included. So here we have b and then all the way to negative infinity. And that's the again the indication that this continues indefinitely. And again, notice that infinity, or minus infinity in this case, also has a parenthesis. Again, it never has a bracket. Similarly, when we include the point b, from minus infinity to b included, then we have the set of all x such that x is less than or equal to b. That would be the set notation. And in the graph of it, we have now a bracket here because the endpoint b is included, and then the line goes all the way to the left to minus infinity. And then last but not least, when we have the interval from minus infinity to plus infinity, again parentheses. In set notation, that is the set of all x such that x is the real number. And so we just have the real number line indicated with a line with arrows on both ends going in both directions, in each direction indefinitely. So that's a notation that we'll be using for indicating what the solution to an inequality is. And so we just have to pay attention to what the problem statement says, in which form the solution is to be presented. For the next few exercises, we are asked to write an interval notation, the given set or graph. So here, here we have the set notation, and so we're supposed to write it as an interval. And so here the set notation says the set of all x such that -4 is less than or equal to x less than 5. So that means in interval notation, we include the endpoint -4 because it's a less than or equal, and then goes to 5, and then it has a parenthesis because 5 itself is not included. It's strictly less than 5. So that would be the solution to this interval here. So -4, 5. You can just do it on this piece of paper. Here, the set tells us the set of all x such that x is less than or equal to -2. So that's an infinite interval. So we start on the right side. It's a -2 included, and then it goes all the way to the left to -infinity. And then, of course, gets a parenthesis. So here, the number 6, we have the set of all x such that 6 is greater than or equal to x less than greater than 2. So what might that look like? Well, there would simply be the interval from 2 to 6, where 6 is included, because we have a greater than or equal, so the equal sign there. And here we're looking at an interval. In graph notation, we're supposed to write that in interval notation from 10, x, the set of all x such that x is greater or equal to 10, and that's all the way to positive infinity. So that would be the following interval. So we begin at 10, and then it goes to positive infinity, and again that has a parenthesis. And here for number 8, here we have a closed interval from -30 to +30. So that would be the set of the interval from -30, and it has a bracket because it has a bracket here, and that means -30 is included. Similarly, positive 30 is included also in the interval, and there would be the interval notation for this graph. Next, we will talk about the addition principle for inequalities. So when we have real numbers a, b, and c, then a less than b is equivalent to a plus c less than b plus c. In other words, when we add the same quantity to both sides of an inequality, we've got the same inequality. In other words, we have the same solution set. Similar for the inequality a greater than b. When we add c to both sides, we have the statement a plus c is greater than b plus c. And then similar statements hold for less than or equal and greater than or equal. So in other words, that's just the same thing that we did when we solved equations. This addition principle holds also true for inequalities. And of course, we use these principles to solve inequalities, and we'll do some of that in just a moment. Let's apply the addition principle for inequalities to this particular example, number 9. So x plus 6 is greater than 9. Remember, it's always about isolating the variable. So by subtracting 6 from both sides, so 9 minus 6. Then we get on the left side x plus 0 is simply x greater than, and 9 minus 6 is 3. So that is our solution to the inequality, to a given inequality. And that means we now look at the interval, or the set of all x, such that x is greater than 3. So now we have the solution in set notation. And when we graph it, we will simply do it on this existing graph here. So it's greater than 3. And so we simply draw a line to the right of 3. And that is the graph then of the solution for this inequality. So here's set notation, and here's the graph. And of course, in interval notation, it means 3, infinity. And again, infinity with a parenthesis. Similarly, when we look at number 10, x plus 4 less than or equal to 7. So x plus 4 less than or equal to 7. By subtracting 4 on both sides, we isolate x. So x plus 4 minus 4 is less than or equal to 7 minus 4. And that then becomes x is less than or equal to 3. And so in interval notation, we have 3 here with a bracket. And it goes all the way to the left to minus infinity. And that gets a parenthesis. So this is our interval notation. And in set notation, it would be the set of all x such that x is less than or equal to 3. So that's set interval notation, set notation. And for the graph, we just use this graph paper here. And so there would be, we start at 3 with a bracket, and then it's all the way to the left, all the way to minus infinity. So we draw a line this way here. And put an arrow at the end, and it will be our graph. And again, this is a bracket. It has a bracket because it's less than or equal to 3. For number 11, we just have to solve and graph the inequality here. So it begins with the statement 2x minus 3 is greater than or equal to 3x minus 1. And so we are kind of led along the way here what you're supposed to do. And so 2x minus 3, and we're going to subtract 2x on both sides, so minus 2x. And so we have 3x minus 1 minus 2x on the other side. So then 2x minus 2x is 0, so we only have negative 3 on the left side. And on the right side, we have 3x minus 2x, which is x. Then, to isolate x on the right side, we add 1 to both sides, because minus 1 plus 1 is 0. So we need to add 1 to the left side also. So that gives us, on the right side, simply x, because minus 1 plus 1 is 0. So that's where the x comes from. And then minus 3 plus 1 is minus 2. So in other words, minus 2 is greater than or equal to x, or we can turn that around and write that as x is less than or equal to negative 2. So the solution set is then the set of all x such that x is less than or equal to negative 2, or in interval notation, minus infinity to minus 2. And as a graph, we start at negative 2. And we draw a line to the left of minus 2. and with the arrow to the left symbolizing minus infinity. So an arrow here. And again, this is a bracket here at minus 2. I hope this last example gave you a clear idea how to proceed step by step. And even though there are different ways to get to the same answer, maybe you want to try it out and see if you can use a different approach and still come up with the same answer. So, but anyway, this is one way to get there. So the addition principle for inequalities was exactly the same as that one as it was for equations. Now, when we talk about the multiplication principle for inequalities, we got to be a little bit careful. So first of all, there are two cases. For any real numbers a and b, and for any positive number c, so the emphasis is positive, if a is less than b, that's equivalent to ac less than bc, b times c. Or if a is greater than b, then that's equivalent to a times c is greater than b times c. So that's like what we did for equations as well. However, here's the difference, and really pay attention to this. For any real numbers a and b, and for any negative number c. So here it's a little bit different when we multiply an inequality by a negative number. That is key. So multiplying by a negative number or dividing by a negative number is the same thing in principle. So if a is less than b and c is a negative number, then a times c is greater than b times c. In other words, the inequality symbol gets reversed when we multiply or divide by a negative number. The same way when a is greater than b and c is negative, then ac is less than b times c. So we need to turn the inequality symbols around, no matter what they are, when we are multiplying or dividing by a negative number on both sides. So, and then of course similar statements hold for less than or equal and greater than or equal. So in every case where we multiply an inequality by a negative number or divide by a negative number, remember to turn the inequality symbols around in the opposite direction. So let's apply the multiplication principle to this inequality here. So here we have 5y is less than or equal to 3 divided by 2. So to isolate y, we need to divide both sides by 5. So then 5y divided by 5 is less than or equal to 3 halves divided by 5. So that here the 5 would now cancel, and so we have y less than or equal to 3 halves times 1/5. Or finally we have y less than or equal to 3/10. Okay. In other words, now in set notation, we have the set of all y such that y is less than or equal to 3/10. That would be in set notation. And in interval notation would be minus infinity, comma, and then 3/10 with a bracket. And in the graph, we have the number line already here. So 3/10 is approximately here. And of course that gets a bracket, 3/10. We're going to write 3/10 here to make it clear. And then we graph a line to the left. And that is our solution set in form of a graph. Let's do number 14. So here we have minus 1/3 x less than or equal to negative 4. And to isolate x, we need to multiply minus 1/3 by minus 3. So we have minus 3 divided by 1 times minus 1/3 times x. And then we need to multiply minus 4 by minus 3 also. And now we need to remember to turn the inequality symbol around, because we're multiplying by a negative number on both sides, negative 3 in this case. So minus 3 divided by 1 times minus 1/3 is 1, or simply x. And x would be greater than or equal to, and minus 4 times minus 3 is equal to positive 12. So x is greater than 12. And then in set notation, excuse me, there would be the set of all x such that x is greater than or equal to 12. And in interval notation, there would be from 12 to positive infinity. And remember, that gets a parenthesis. And when we graph it on the graph above a number line here, so we start at 12 with a bracket. And we graph a line all the way to the right to indicate symbolically positive infinity. So here we have the step-by-step solution. We have the solution set in form of a set, in form of an interval, and in form of a graph. And here's an example of another guided solution. So we begin with the inequality 6 minus 5y is greater than or equal to 7. Then to isolate the term with the variable on the left side, we subtract 6 on both sides. So 6 minus 5y minus 6 is 7 minus 6. Now on the left side, 6 minus 6 is 0, so we only have minus 5y on the left side, greater than or equal to 1, because 7 minus 6 is equal to 1. Now we divide both sides by negative 5, so it's a negative 5 here. And because we are dividing by a negative number, remember to change the direction of the inequality symbol, so now that becomes a less than or equal. And minus 5y divided by minus 5 is simply y. And on the right side, we have minus 1/5. And let me just make a little remark in between, because some people are confused by that. As far as fractions are concerned, minus a divided by b means minus a divided by b, or a divided by negative b. Okay, these are all equivalent expressions. So whether it's a minus 5 in the denominator, we can rewrite it, and it's commonly done with a minus in front of the fraction bar. So be sure you understand this transition here. That's why I brought this up here. Okay? Okay, so then we have the solution set, the set of all y, such that y is less than or equal to minus 1/5, or in interval notation from minus infinity to minus 1/5 with a bracket. Number 16, 3x plus 5x would be 8x less than 4. We divide both sides by 8, so then x is isolated, and x is then less than 4 divided by 8, or x is less than 1/2, reducing this fraction here. So that means the set of all x in such that x is less than 1/2. And in interval notation, it would be minus infinity to 1/2, and where the 1/2 gets a parenthesis because we have inequality here without the equal sign. In example number 17, we've got to use several properties here. And so we begin with eliminating the parentheses. So we have 17, and minus 5 times y is minus 5y. And minus 5 times minus 2 is positive 10. Less than or equal to 45y. And now we have 8 times 2, y would be 16y. And 8 times negative 3 is minus 24, minus 39y. And as we collect like terms, 17 plus 10 is 27, minus 5y, less than or equal to so on the right side, 45y plus 16y minus 39y would be 6 and 16 would be 22y minus 24. And now when we add 5y to both sides, we have 27 minus 5y plus 5y less than or equal to 22y plus 5y minus 24. So we have on the left side, we have only 27, less than or equal to 27y minus 24. So we add 24 to both sides, 27 plus 24, less than or equal to 27y minus 24 plus 24. So that gives us 51 less than or equal to 27y. Now we divide both sides by 27. And so then we have 51 divided by 27 less than or equal to y. And this reduces to 17 divided by 9 less than or equal to y. Or we can say y is greater than or equal to 17 divided by 9. And then the solution in set notation would be the set of all y, such that y is greater than or equal to 17/9. And in interval notation, it would be 17/9 with a bracket, comma, positive infinity with the parenthesis. So these are the solutions to the initial inequality. Next, we're going to look at words and how they translate into inequalities. And in many problem solving and applied situations, we need to do that. And so, is at least or is at most? That means, for example, Max is at least 5 years old. So if M is Max's age, that means M is greater than or equal to 5. Or at most 6 people could fit in an elevator. N is the number of people that fit in an elevator. N is less than or equal to 6. Or cannot exceed. So now we're talking about something has to be less than or equal to a certain amount, or in this case weight. Or must exceed. The speed must exceed 15 miles an hour for some reason. And so S is the speed, must exceed, must be greater than 15 miles per hour. And Heather's income is between $23,000 and $35,000, presumably per year, even though that doesn't matter. But so it means that, if H stands for Heather's income, so it's between greater than 23,000 and less than 35,000. It's between. So the endpoints are not included. That's why we have inequality. Or Bing weighs no more than 90 pounds. That means his weight is less than or equal to 90 pounds. And Saul would not accept less than $4,000 for the piano, that means it's got to be at least or more. So in other words, P, the price of the piano, would be greater than 4,000. So it takes a bit of practice to translate these words into inequalities, and that's what we'll do here in the next few minutes. So here's kind of a subset of what we just talked about, translating at least and at most. A quantity x is at least some amount. That means x must be greater than or equal to that amount, in this case q. So in other words, if x is at least q, it cannot be less than q. That's the logic behind it. Similarly, a quantity x is at most some amount q, then x is less than or equal to q. In other words, if x is at most q, it cannot be more than q. So it has to be less than or equal to q. So let us apply what we've just learned to some simple examples. So we're going to write inequalities now. Russell will pay at most $250 for the plane ticket. So if T is the cost of the plane ticket, that means then T is less than or equal to 250. Okay? And number 19, Emma scored at least an 88 on her Spanish test. So if Emma's score is S, and at least means greater than or equal to 88, that would be the corresponding inequality. And the time of the test was between 50 and 60 minutes. So if T is the time of the test, we are told it's between 60 and 50 minutes. And the University of Southern Indiana is more than 25 miles away. And if D is the distance, that means then D is greater than 25. It's more than 25. And at number 22, Sarah's weight is less than 110 pounds. So if W is Sarah's weight, then W is less than 110. And that number is greater than -8. So if N is that number, greater than -8, there would be that inequality. And the cost of the production, the cost of production of the barcode scanner cannot exceed 135,000. So that means if C is the cost of the barcode scanner, C would be less than or equal to 135,000. So these are just some very simple examples for writing inequalities. Here's the last example. Salary plans. A painter can be paid in one of two ways. Plan A, $500 plus $4 per hour, or a straight $9 per hour. Suppose that a job takes n hours. For what values of n is plan A better for the painter? Okay, so let's define the terms here. So n is the number of hours for which the painter will get paid, number of hours. And so we are told that plan A would be $500 plus $4 for every hour. So 4 times n, or 4n. And plan B is simply $9 per hour, or 9n. And so the question is, for what values of n is plan A better for the painter? So in other words, plan A better than plan B means this. So that means we now ask the question, 500 plus 4n, which is plan A, for what values of n is that better than plan B, which is 9 times n. So we need to solve this inequality here. So we begin by subtracting 4n on both sides. So 500 plus 4n minus 4n greater than 9n minus 4n. So then On the left side, we only have 500 left. So 500 greater than, and 9n minus 4n is 5n. Dividing by 5 on both sides, so 500 divided by 5 is greater than 5n divided by 5. So we have 100 greater than n, or n less than 100. So when n is less than 100 hours, it's plan A is better for the painter. And so we state our solution set, the set of all n, such that n is less than 100. For and plan A is better. Plan A is better. Now notice in this case, if we do a solution set, we're not going to go to minus infinity, because n, the number of hours, is greater than or equal to 0. So if we were to graph it, then the inequality would, the error would only go to 0. Okay? So anyway, just be aware of certain applications where we're dealing with certain realities, like the number of hours cannot be a negative number, obviously, and it cannot certainly not go to infinite, not minus infinity either. Anyway, that's a solution to this particular problem. And that's the end of section 1.4.